I have to start by apologizing because usually I try to explain everything in great detail, very slowly, and so on. This time, I have to rush into the hardcore category theory because I want to get to a certain point and I have to stick it in within 45 minutes, so bear with me. It's okay, if at some point things get so confusing that you stop understanding, and it's perfectly normal. In category theory, it's always like this, you understand things to a certain level, and then the next level seems like a totally weird thing. But once you get exposed to it, things clear out after a moment. So I'm just going to jump directly into profunctor optics. So I don't know, I will explain some of the terms, but not all of them. So here's a definition of a lens and a prism. And notice, okay, so first of all, for all, this is Haskell, okay? For all means it's a polymorphic function. It means that it will work for any P, okay? But what is P? You see, P is acting on A and B on the right-hand side. You say P, A, B, P, S, T. A, B, and S, and T are types. So this is just like taking types and producing new type. Okay? A profunctor is a generalization of a functor, takes types and produces a type. So P is really what we call type constructor, because it takes types and produces types. Okay? So when I first saw this kind of formula, I was really puzzled because so this works for any profunctor. It's like you generalize whatever profunctor you give me, it'll work. And it's a function that takes this type PAB, which is generated from two types A and B, and produces a new type, an element of a type PST, which is produced from S and T. Moreover, so this is not all. There is also this strong P and choice P. These are the constraints. They say that this is not just any profunctor, but this is these are profunctors that actually satisfy certain constraints. Okay? But the important part of this, and this is why it's so useful, is that this is just a function. You see, this is a function from PAB to PST. It's like a simple function. And the beautiful thing about functions is that you can compose them. So if you have two functions like these, one is going from PAB and the other is going to PST, and you have another that goes from PST to some RZ, whatever, you can just compose them. And this is why lens is composed with this dot in Haskell at least, because this is like function composition, just simple function composition, right? So this is a great representation for composing lenses. So lens just gives you a view into a sub-object of some object. If you compose it with another lens, it will give you a sub-object of the sub-object, and so on. You can go as deep as you want, telescoping into a data structure. So prism is almost identical, except that it has different constraints. It's called choice. And here I wrote these two constraints. So if P is a profunctor, then strong means that this profunctor supports this polymorphic function from PAB to PA comma C. That's a pair AC. So it's a Cartesian product of A and C, right? And BC. So it means that if P is, you can think of a profunctor as a relation between two types. Okay, that's like one of the ways of imagining it. If P if A is in a relation with B, right? And then also PAC will be in relation with PBC. What does it mean? That if you have a data structure that can be decomposed into A and some rest called C, then you have a relation with B and this rest C as well. So A and B are these sub-objects, and C is like the environment in which they live. Okay, so that's the intuition behind it. Now, choice is almost identical, except that instead of a Cartesian product pair, it has the either, which is Cartesian, co-Cartesian product, or some type, right? But other than that, it's very similar, right? And the definition of a profunctor is that it's sort of like a functor, but it can, a functor can lift one function at a time. Profunctor lifts two functions at a time, from A to B and from C to D. But the funny thing is that A and B are kind of inverted. You see, PBC goes to PAD. That's an important thing about profunctors. Okay, so now let me show you some pictures. Okay, let's start by refreshing some ideas about functors. So a functor in category theory is just a mapping between categories. So if you have an object A, look at this picture. You have an object A in one category, you map it into an object FA in another category. You have object B, it's mapped into an object FB. But in a category, you also have these arrows. Think of them as functions for the time being, right? So you have a function from A to B, then a functor will also give you a function from FA to FB, right? So this is the definition of a functor in Haskell. It just says that if you have this type constructor F, type constructor means mapping types to types, so it's a mapping of objects. Fmap maps functions to functions, right? Takes a function from A to B, gives you a function from FA to FB, okay? Profunctor, that's this picture, does it with two categories at a time, okay? So it takes two objects, one from one category, one from another category. I mean, in what follows, we'll stick to the same category, but it doesn't matter. I mean, in principle, this could be different categories. So it takes two objects, A and C, and creates a new object, PAC, or new type, PAC. So it's a type constructor that takes two arguments. It takes B and D and produces PBD, right? Now, the lifting of functions is funny because it takes a pair of functions and lifts them, right? But one of the functions goes in the opposite direction. Because you can think of this as it's consuming one type and outputting another type. So when you're consuming, you have to like adjust the input, right? When you are producing, you adjust the output in the opposite direction. And in category theory, this is just, this is really still a functor, but it's a functor from a product category. And this little op means that it's an opposite category. An opposite category means that all the arrows are reversed. This is why we have the reversion of where the function goes. Okay? So this is the introduction. Now, when you have two functors, okay, you can now think about, okay, can I map one functor to another? And the mapping between functors is called a natural transformation. So X is an object in some category, right? Fx is the mapping of this object into the category using the functor f. Gx maps using functor g. So we have two functors, right? We have two functors. And since these functors go into these two objects, fx and gx, we can pick a function from fx to gx. For every object x, if we pick a function like this, then we get a natural transformation. What does it mean to pick a function for every object or every type? It means you have a polymorphic function, right? It's a function that works for any type. So in Haskell, you can define this type of natural transformation, the squiggly arrow, as for all x. So for every object x, it's a function from fx to gx. That's a polymorphic function. I mean, this for all x usually is omitted because Haskell figures out. But it's a definition of a natural transformation. And here's an example of natural transformation that transforms a list functor, list is a functor, and maybe is a functor, optional for Scala people, right? And it's defined that on an empty list gives nothing, and on a non-empty list it just gives the first element of the list. So it's a safe way of taking the head of the list, right? But it is a natural transformation between these two functors. There is some commuting diagram that goes with natural transformations, but I'll skip that part, okay? So now that you see what, look at the natural transformation. It has this for all x, right? So it's sort of getting similar to the lens, but a lens is for all p, strong p, PAB, PST. Okay, so when I first saw this, I was thinking, okay, but this looks like a natural transformation, but it's between something else. I mean, this is like a different category. How can you have a natural transformation where you have profunctors, right? And then I figured out that the only place, I knew very little about category theory, but I knew the Yoneda lemma. And the Yoneda lemma is one place in which you have this for all. It's just like a pattern recognition. Okay, here's for all, here's for all. Then maybe Yoneda lemma is relevant to figuring out the lens, okay? So let me explain what a Yoneda lemma is. So Yoneda lemma says that there is this special functor called the reader functor that is just a type of a function from a to x. So it's a functor in x. A is just a parameter. There are two types, a and x, right? It's actually a profunctor, but it's looking just at the x part. It's a functor, right? And here's the definition of why it is a functor, instance functor. I can define fmap for it, how to lift a function, right? Now, Yoneda lemma says that if you have any functor f, then first of all, you can get to this functor f from the reader functor. So reader functor is a very special functor because it has natural transformations to every other functor. And the set of these natural transformations between these two functors. So now remember, two functors, natural transformations, which is a polymorphic function, between two functors, right? The set of these natural transformations is equivalent to the value of this functor at the object A. Okay? And here below it's written as a natural transformation. Natural transformations for all x. This is the reader of x. This is fx. And this is equivalent to f of a. Now, quickly, the intuition behind this. The left-hand side is a function that takes a function. Okay, so it's a higher order function, which is polymorphic in x. The right-hand side is what we call data structure. It's like, okay, it could be a list, right? Take type A, you get a list of A. So there are two very different representations. One is what we normally call data. The other is function, a polymorphic function, polymorphic higher order function. These two representations are totally equivalent. And this is what is great about the Yoneda lemma in programming, because sometimes you want to use a different representation for your data type for performance reasons or for reasons like in this case it will be because it composes better. Okay? So that's a great point of Yoneda lemma. And here's a little proof that the Yoneda lemma works, and actually it's kind of in Haskell it's almost trivial why this should work. Okay? But I'm not going to go into the details in there because I'm interested in the special case of Yoneda lemma where the second functor, so it's a natural transformations from a reader functor to some arbitrary functor f. I can replace this arbitrary functor f in particular with another reader functor, right? And then I get this formula at the bottom, which is the Yoneda lemma for the reader functor here, right? It's a different reader. It's a reader from B. The first reader is from A. The second reader is from B, right? And if I so this is my fx, right? If I replace x with a on the right-hand side of the Yoneda lemma, I will get fa is function from B to A. All right? So it's B to A. So this is a really a huge simplification. You have like a function that takes a function and returns a function, and it's polymorphic in X, and it's totally equivalent to a function from B to A. Notice that they are reversed. Like A is here, B is here. Here they are reversed. And this is called, well, this is just a special case of Yoneda lemma, but it's used in so-called Yoneda embedding, so I call it Yoneda embedding. And now, remember, I wanted a polymorphic thing that's polymorphic in profunctors. So let me make the next abstraction and say, okay, how can I use a Yoneda lemma so that the for all actually takes a functor rather than a type? Well, from the point of view of category theory, that's a very simple thing, you know. Functors form a category. What kind of category it is? Functors are objects in this category, and arrows in this category are natural transformations that I mentioned before. Because natural transformations go between functors, okay? So they form a nice category. And since they form a nice category, the Yoneda lemma applies to them as well. So I can take the same Yoneda lemma, replace my x with a functor, and replace my functions with natural transformations, and I get a Yoneda lemma in the functor category. So above is Yoneda lemma. Here's the Yoneda lemma in the functor category. You see what changed? I just renamed these things so that they look more like functors. I replace them A and X with G and F, right? And I replace arrows with squiggly arrows, right? Which is natural transformations. So the mapping from natural transformations between functor G and F, there's a natural transformation between functors H and F, and the result here, this is equivalent to a natural transformation from functor H to G, okay? And I have finally this for all F where F is a functor, okay? So I'm getting very, very close to lenses, but not quite yet, right? But let's use this little example, okay? So my first approach is let's construct a toy optic. You know, so something really, really simple, right? And so the trick here is I want to create a very simple optic. So I start with the Yoneda lemma in functor category. That's the top line, right? Now, These squiggly arrows are natural transformations. So I'm just writing them explicitly using for all, right? So a natural transformation from G to F is for all x, gx to fx. I replace the second one and the third one. So this is just a trivial substitution, like definition of natural transformation, right? And now here's the trick. I can pick, for G and H, I can pick anything I want, okay? Any functor. Well, in particular, I can pick a reader functor, again, right? This is like a standard trick. Just pick a reader functor. So gx is a reader functor based on A, hx is the reader functor based on S. I replace it, and now look what happens. In these internal for alls, I have reader from A mapped to fx. But that's Yoneda. Again, reader functor mapped to fx. This is a natural transformation from the reader functor. I can replace it with fa. Here I can replace it with fs. And at the bottom I can replace it with a reader from from A to S, right? So after rewriting this, here's the final result. Okay? And I can say this is type toy lens, parameterized by SA, for all f, where f is a functor, fa to fs. So that looks very much like, like if you squint, this looks very much like one of these profunctor lenses, except that with a functor, right? And I'm showing that this is equivalent to just a straight function from A to S. Okay? So I don't know if you see the pattern here. It's like this is sort of the representation, this sort of like profunctor optics type of representation, and this is the like simple implementation, like a lens can be represented by setter and getter, right? This one is just a getter, right? It just gets S out of A. Very simple. So I'm on the right track, right? But now I want to do this for profunctors. So Yoneda for profunctors. But profunctors are really, from categorical point of view, they are simple. They are just functors from the product category, C up, C to some other category, right? But I have to like rethink things a little bit, like what's an object in a product category? It's a pair of objects. What's a morphism? It's a pair of morphisms, right? So I will start working with pairs. And what's a reader in this category? Well, it will be a pair of functions, right? Like a reader was a function type. This is a pair of function, except that the first function goes in the opposite direction. So I have a pro-reader from a pair AB to a pair XY. And it's a pair of two functions. Y goes from X to A, and the other goes from B to Y. The first one is in the opposite direction because it's a profunctor. It's the opposite category. That's why, right? Yeah, and the second line just shows that pro-reader, this guy, is actually a profunctor because I can lift a pair of functions, one by prepending, one by propending, right? And pro-Yoneda is, again, the same thing, except that now I have to work with pairs of objects. So instead of for all x, I have for all xy, and I have a pro-reader, so a pair of functions, goes into a profunctor, arbitrary profunctor pxy. And pro-Yoneda says that, this pro-yo of PAB is isomorphic to PAB. So now, again, I have a representation of a profunctor, which is like this data type, kind of, in terms of a polymorphic function or a natural transformation, right? So this is the bottom line. It's just rewriting it in this form. For all xy, I have a pair of functions. I just uncurried them and curried them and going to PAXY, and it's equivalent to PAB. So this is really just substituting one thing for another and just figuring out, oh, the direction of arrows have to be changed and so on. But it's pretty much trivial. Now, that was a Yoneda for profunctors. Now I want to do Yoneda on profunctors. I want to go to a profunctor category. Profunctors also form a category, okay? They have natural transformations that are sort of like these two natural transformations that take pairs, right? So there are pairs of functions. But the idea is exactly the same. So I have natural transformations. And this is what it is, you know. This is like the Yoneda lemma on profunctors. I replaced some letters with P and Q, and I replaced arrows with squiggly arrows, right? This is actually the kind of Yoneda embedding version of the Yoneda lemma, right? And below I rewrote it using the definition of what is a natural transformation, what is the squiggly arrow for profunctors, right? So it has for all xy, qxy, pxy. And now I have finally my for all p, okay? That's the big step. I have for all p, so I'm close. And I use the same trick as I did before. You know, I replace q and r, which are free parameters in this formula. I replace them with my pro-readers, right? So I put pro-readers here, and when I put pro-readers in here, I get a Yoneda lemma for profunctors, right? So I can reduce this. I can replace x and y with a and b, and I replace xy here with s and t. You know, these are different x and y's. They are scoped within the for all, right? So if I do this, I can now perform the Yoneda again, and I get this formula. For all p profunctor p, PAB, PST, okay, that's my optic, profunctor optic, right? And from this double application of Yoneda lemma, I get that this is actually QST, but my Q is A to X, Y to B, okay? So I just wrote this explicitly, so this is a pair of functions from A to S and a function from T to B. And if you've seen profunctor optics, this is the definition of ISO, okay, in the Haskell library. So like this is the simplest profunctor optic that there is. But I'm still not getting lenses and prisms, right? So what's the next step? The next step, so this is what it looks like. So I got the first line, ISO, okay? That was kind of easy. But now I want to generalize it to get lens and prism. But lens and prism have these additional constraints, right? Strong and choice. And if you notice that there is a very similarity between strong and choice, it's just replacing Cartesian product with what is called coproduct, the sum type, right? So there is actually a categorical thing that generalizes product and coproduct at the same time, and it's called a tensor product. So a special case of a tensor product is Cartesian product and Cartesian coproduct. Hey, so I can just say, let me go totally general and combine lenses with prisms, right? And in category theory, something like this is actually called a Tambara module. Okay? So this is the definition of Tambara module translated to Haskell, right? So I just replaced pair and either with this tensor product. And that's it. So now I can work with prisms and lenses at the same time. But how do I get, I have to go through adjunctions, okay? So Runar explained the adjunction, so I don't have to, right? So when you have two functors, and I actually have an example that's exactly like Runar's, okay? The adjunction between pairing and function space, right? So I have a functor f going from A to FA. Okay, I have a functor u that takes B to UB. If these two sets of arrows are isomorphic, then I have an adjunction, okay? Which means sort of that instead of preparing the initial state using f, I can modify the final state using u, okay? So like you have functions, and they are in one-to-one correspondence, the ones that I prepared the input and the ones that I modified the output. But of course, the preparation of input and the modification of the output have to match magically, and that's called the adjunction, right? And because of this adjunction, this particular adjunction between Cartesian product and the function space, right? This is called currying. There is a version of Yoneda lemma, it's called co-Yoneda lemma, that works like this. And this is an existential quantifier, right? Haskell does not really have a notation for existential quantifier, but you can fake it using a universal quantifier. So I won't go into detail, but this notation actually is useful. So there exists an X. So I have a data structure in which X is hidden, right? I know there is an X, but I don't know what it is. Somebody gave me this data structure. It's like data hiding, right? And it contains fx, which is like a container of x's, functor acting on x. You can think of it as a container of x's. And there is a function from x to a. And even though I don't know what x is, there's one thing that I can do with this. I can f-map this function over this container. And what happens? I get fa, right? So this is the co-Yoneda lemma in a nutshell. So these two data structures are equivalent. So now I want to do a Yoneda and combine it with adjunctions, right? So I wrote the Yoneda lemma above it. And remember, A and B are just arbitrary parameters. There are external things. I can pick something from A and pick something for B, okay? So the clever pick is to replace A with FA and replace B with FB, where F is a some functor that is enjoined to some U, okay? So if I replace them, I can then use the adjunction, because I can say instead of preparing A with F, I can I can modify X with U, right? Because these two are in one-to-one correspondence, right? Because of the adjunction. And the same here and the same here. So I did this adjunction, I performed this adjunction, right? And the result of this, okay, if I do the adjunction also in the result of this identity, I get a function from B to U combined with F acting on A. Now, these are two functors. A composition of functor is again a functor, right? And this composition of two adjoint functors is actually a monad, and Runar also explained that, okay? So this is Yoneda with adjunctions, and I just want to do the same thing, but in profunctor category, okay? So now, a functor in a profunctor category means it takes a profunctor, maps it to another profunctor, right? Takes a natural transformation, maps it to a natural transformation, okay? So this is at the top, it's just repetition of the Yoneda lemma in Profunctor category, right? And this is what we get applying it, right? So I have just rewritten the Yoneda lemma, right, in the Profunctor category. So the only change is that I suddenly have this U here, right? I started with something that was with P, with F, and I put a U on the right-hand side using the adjunction, right? So this is like the same formula as before, except that I replaced things with profunctors. Right? Now, what are the two categories in which I'm working? That's very important, okay? I'm working with the Tambara category, in which my profunctors are actually Tambara profunctors, which means these are these profunctors that have this additional structure. They have this mapping, right? This mapping from PAB to PA cross C, B cross C, right? U is, I pick as U as a functor that is a forgetful functor. Runar also talked about this. Forgetful functor just forgets the structure. So if I have a profunctor that's a Tambara profunctor, I can map it into the category of profunctors, sort of the same profunctor, but forgetting that it has additional property. I'm just forgetting about this property, nothing else. But there is an adjoint functor that will take any profunctor and make it a Tambara profunctor. It's called a free functor. Free functor takes something without structure and makes additional structure on top of it. Okay? So, this is my formula for the Tambara mode. And I say Tambara P. So I'm working in the Tambara category, right? And this is suddenly becoming very lens-like, because the Tambara constraint is exactly what we need for combining lenses with prisms, right? So here it is, this formula from the previous page, right? And now I'm doing the identical trick as before, right? I'm replacing Q and R with the pro-readers. Then I do the internal Yonedas, right? And I end up with this. Okay, so the line before the last one, the line before the last one still has these U's, right? But this U means that I take a profunctor with some structure and I map it into a profunctor without this structure. But it's the same profunctor, right? It's really the same profunctor. I can skip U in Haskell. I can just skip it. It doesn't do anything, right? It's a forgetful functor. It takes a functor that has some structure but makes it like a regular functor without doing anything, right? So I have suddenly, for all P, Tambara P, PAB to PST. So this is exactly what I wanted. This is my profunctor optic that combines lens and prism. Now let me look at the right-hand side. Okay, right-hand side has this U F, right? And I said this is a monad. So I call this monad F, phi. Now, I'm not as smart as to figure out what phi should be, but there is a paper by Pastro and Street that actually dealt with Tambara modules, and they came up with a formula for phi, okay? So in categorical language, this is like, it's a coend. This integral sign means coend. This is like a tensor product, whatever it means, it can be translated into Haskell very simply. A coend is translated into existential types. Right? An AND is a universal, coend is an existential type. So it means exists C, X, and Y. These three things that are multiplied there, they are just a standard tuple, because we are now working in set. So it's a tuple of three things. So it's a pair. And AS, that's a home set, which is really a function from S to C cross X, from C cross Y to T. So it's a pair of functions, and then it's QS. So the property that this phi has is that you give me any profunctor Q, whatever profunctor you give me. The result, phi Q, is a Tambara profunctor, automatically. Okay? It freely generates a Tambara profunctor. Okay? Now, if you remember, in the substitution, I replaced the profunctor there, the R and Q, I replaced them with the pro readers, right? So I have to apply this phi to a pro reader, right? And if I apply this functor to a pro reader, so the QXY is a pro reader, right? So I replaced Q with this. And then I can use the co-Yoneda lemma to eliminate this Q. Because this Q is just a pro reader, right? Q becomes a pro reader, and the pro reader paired with something like this and exists CXY, exists XY, this is just a co-Yoneda lemma. So I can replace X and Y with A and B. Okay? So I get phi QST exists C, and this is I'm just left with this pair of functions from S to C cross A, from C cross B to T. Okay? And now I'm just rewriting this formula for two different tensor products. The first one is a pair, right? And I get a lens, right? Because I get a lens STAB. After doing the Yoneda, I get this exists C, that S goes into CA, CB goes into T. Do you recognize this as a lens? It says that the whole data structure S can be split into a product of some C, the environment, and the focus A. And again, if I have C and the focus B, then I reproduce T. So that's an existential definition of a lens. And prism is exactly the same thing, but I replace the tensor product with either, right? And this is what I get. So that shows you that the profunctor representation of lens and prism can be directly translated into our standard, version of lens and prism using a pair of functions. Okay? This is the picture that illustrates it, right? That's the lensing, and that's it. Okay.